Good day to you all. I am Niranjan Meegammana together with Harin Fernando and Vishwakumar from Sri Lanka Institute of Information Technology and Shilpa Sayara Foundation. We are going to present AI-driven anomaly detection for climate hazards in Sri Lanka using CNN-LSTM autoencoder models. The background and the problem: Sri Lanka faces frequency floods, storms, and landslides, intensified by climate change. Traditional models rely on label data and manual features, which limit scalability. Lack of real-time, high-resolution datasets constrains accurate early warnings. Our goal: develop label-efficient AI system for detecting pre-disaster anomalies. Literature review. We studied deep learning, CNN and LSTMs, which enables spatial temporal feature extraction. Prior studies achieved strong spatial accuracy, but limited temporal modeling. Most models depend on large annotated datasets, which are unsuitable for Sri Lanka. Research gap: unsupervised multimodal approaches for hazard detection. Methodology and data. Our data sources were weather, ERA5, and CHIRPS, which provide rainfall, temperature, humidity, and wind data. Satellite, CIMS tropical cyclone imagery, which provide brightness indices. Disaster labels, UNDRR, Dell, Inventor. We covered 21 cities from 2018 to 2025, data spanning over 7 years. We used 8-day sliding windows for temporal modeling of environmental dynamics. Our methodology and data preparation. We obtained the satellite data and select a window and created a 160 by 160 scale image and reduce it to 128 by 128 size to meet CNN requirements. Then we broke them into channels and obtained the brightness. The temporal data using the sliding window structure provided us this kind of a data distribution, where rainfall data and the disaster frequency is shown in the graphs on the right. The deep learning pipeline involved weather data from Google Search Earth Engine, disaster data from OCHA, and climate images from CIMSS. Preparation and merging. Then we input them into LSTM and CNN autoencoder model. It's a hybrid. Training and testing evaluation, and trained AI models to provide hazard detection, which included 7 days current weather satellite images. The model architecture. It's a CNN LSTM autoencoder pipeline. CNN captures short-term spatial trends. LSTM layers model long-term temporal dependencies, trained only on normal data to reconstruct expected behavior. Anomalies are obtained from creating high construction error. So we had to do reconstruction to get a better accuracy. The hybrid architecture visually is like this. The encoder, when input into 8 days, 13 features, weather and disaster satellite image sequence, the encoder used conventional 1D 8 by 64 layer, 8 records. Max pooling 464. Dropout and layer norm 464. Then we send them through LSTM layer 4 and 64 and LSTM layer 2 and 32. During hyperparameter testing, we tested several models and found this is as a most optimized model. So latent space and decoder provided repeat vector 832, LSTM layers 8 by 32, LSTM layer 4, 864, time distributed dense 8 by 13, and output 8 days and 13 features. Model training and baseline results. We split the data to 70, 10 and 20 split. The 10% used for validation and 20 for testing. We use Adam optimizer with 200 epochs and MSC loss was measured. The baseline performance, F1, we got disaster, which is 0.28, recall 0.99, precision 16, accuracy 60. Detected almost all data disasters, but high false positives. The reconstruction error threshold was 0.12, optimized via F1. Now, why we received this less F1 and accuracy? Because disasters, they don't happen always. So data set is actually in balance when it comes to normal data and hazards. So we use a technique called reconstruction, and through reconstruction, we got high reconstruction errors coincide with disaster date before reconstruction. You can see disasters are in blue dots, and geospatial anomaly plots show clusters in high-risk districts. This is the latitude and the longitude. That is how the disasters in Sri Lanka distributed over this period. Confirms the ability to learn normal environmental behavior and flag deviations, which are anomalies. Once you reconstruction and rebalanced, we got a better results. We oversample rare disasters sequence through synthetic oversampling. And accuracy increased to 70% and F1 score 0.73. It provided stable convergence and better spatial generalization you can see on the right graph. It allows live anomaly prediction. Conclusion. CNN-LSTM autoencoder successfully models spatial temporal normal patterns. These spatiotemporal normal patterns allow us to predict anomalies in these patterns. HU's label-free hazard detection with reconstruction error and rebalancing demonstrates feasibility for early warnings in data scarcities. Lead Sri Lanka for a AI-enabled climate resilience. This is the first time such a research has been performed about Sri Lankan weather data. And future work, we want to focus on location-based data which were collected from the location itself, because the location-wise, the weather varies. Say Anuradhapura, you collect Anuradhapura data and get the Anuradhapura disasters and train them and predict Anuradhapura. For once we input like 30 days of past data, it will predict 7 days of future predictions. Thank you.